sessions instead of one. And we will be doing a number of problems for each topic, making us familiar with basic parameters, basic machining parameters in different machining processes, and how we can improve the productivity of the machining process by selection of right machining processes. Well, indeed, if we want to talk about machining process, it's a good idea to talk about material removal processes at the larger picture. Indeed, material removal processes are methods which are used in order to bring the part to final shape and geometry by removal of some material from a raw material which has got initial. Could I have the attention of everybody, please? Okay, thanks. Well, in machining processes, indeed in material removal processes, material is removed from an initial raw material in order to bring it to final shape and geometry. Is this generally considered as a desirable manufacturing process? I mean, removal of material from what is produced as a raw material. Is this considered as a desirable method of manufacturing?
No.
Why not?
Because of waste of...
Exactly. That's true. Indeed, we discussed how metallic metals and ferrous metals are produced. We've got to spend a lot of time and money in order to produce raw materials. And eventually, we bring it in the form of, say, bar or plate or something to the workshop, and again start removing material, a material which has been produced at high expense. Now we are removing it, and we are converting it into scrap, something which is useless. So, and we are spending money and time again to convert it into a useful material to something which is not useful. So it's not desirable, is it? To convert a raw material which can be used to make something, and then we are removing material in the form of swarf and chip which cannot be used. And we've got to pay someone to take it away from the workshop. And in order to make that, we've got to make use of cutting tools, electricity, labor, etc., to make that happen. So as a whole, we can say that we are wasting material by making use of machining operations and generally material removal processes, whatever it is. However, sometimes we have to, despite the fact that we don't like it, but sometimes there is no other option, and we've got to make use of a machining process in order to make that happen. Generally, other methods such as casting, forging, and whatever, which can produce the product without removal of material, are advantages compared to machining processes. However, we should realize that there are some advantages found only in machining processes which cannot be found in other manufacturing processes, such as, who can help me with these, such as high accuracy of machine parts, which cannot be found in components made in other manufacturing processes, such as casting, forging, and whatever. High accuracy, high surface finish, tight tolerances. And if we are after high surface finish, higher accuracy, etc., we may need to make use of machining processes despite the fact that we are wasting the material. However, in order to lower the cost as much as possible, it's a good idea to make use of a combination of manufacturing processes. For example, we can make use of casting process in order to bring the part to a a shape and geometry which is close to the final shape and geometry, and leave just a little bit of material to be removed by a machining process. By making use of a combination of manufacturing processes like that, which is of common use in industry, we can lower the cost as much as possible and lower the amount of machining as much as we can. However, still sometimes we are in need of making the whole part by making use of machining processes. Anyway, talking about machining processes, as you can see, machining processes are generally divided into turning, milling, drilling, and some other machining processes which are not commonly used, which are not used as much as the first three machining processes. And we've got some, here in the picture you can see a turning process where the process is used in order to make rotational parts. In this process, as we know, it is the workpiece which rotates, and the cutting tool only has the feed motion, which is taking the cut when the part is rotating. It's familiar to us, right? We have seen it in the workshop, I assume. Right? Everybody? So it's the workpiece which makes the rotation, and the cutting tool only has a linear motion, which is called feed, in order to bring the part to final shape and geometry. In the milling process, which is shown in the second figure from the top, as you can see, this time it's the cutting tool which rotates, and the workpiece is not rotating. Indeed, it is stationary. However, it makes a motion of feed. The workpiece is on the table, and the table makes it move, which is called the feed motion, and the cutting tool, which is rotating above it, can take the cut. And in drilling process, which doesn't need any explanation, every one of us have done some drilling before, right? Have you done drilling, every one of us? Yeah. Everybody. Who hasn't done it? Anybody who hasn't done any drilling so far? Nobody. Okay. So it's we are very well familiar with this method. There is again a rotational cutting tool which rotates after it has got two cutting edges, the cutting tool, and it makes the round hole on the workpiece. These are very well-known operations, of course. And we've got some other machining processes which I have listed here: shaping, planing, broaching, sewing, boring, reaming, and tapping. I assume majority of us are familiar with some of these processes at least, right? Is there any of these methods which is not familiar to any one of us? Broaching. Broaching is not familiar. And how about the other ones? Tapping? Okay. Tapping, reaming. Do we know what reaming is? Reaming, what is it?
It's similar to drilling.
Similar to drilling, a different type of tool is used when a hole is made, but its dimension is not accurate. You know, when you make the hole with a drill bit, you make a hole which has got a dimension close to the final dimension, but it's not accurate, it's not precise. And also the surface finish of the hole is not fine. If we want to improve the accuracy of the size of the hole, and also if we want to improve the surface finish of the hole, then we've got to make use of another tool which is called a reamer. Reamers are used in order to improve the quality of this hole which is already made by a drill bit. So first we've got to make the hole, then we've got to apply a reamer in order to bring it to the actual desired size. And broaching. Who knows what broaching is? Broaching. Well, it's interesting. I'm going to show it to you later on, so let's leave it for another time. And anyway, we are going to cover all of these topics, these processes in this week's and next week's lecture. And non-traditional machining methods. What are they? No, not CNC. CNC is just a modern machine, which is a conventional machine. Non-conventional machining methods are the ones which make use of other, say, forms of energy, such as chemical, thermal, and whatever, in order to bring the part to the final shape and geometry. Mainly in non-traditional methods, non-mechanical processes are used in order to machine the part. However, some mechanical processes are also included in this category. I mean, in traditional methods, a physical operation takes place. A physical process takes place. However, in non-traditional methods, often a chemical, thermal, or whatever process takes place in order to bring the part to final shape and geometry. This is something which we are going to cover for postgrads. One of the topics which is chosen for seminars of postgrad students is non-traditional machining methods. So we are not going to cover this for the undergrad unit, but for postgraduate students we will have some methods covered in this unit. And eventually abrasive methods, abrasive machining, such as grinding, honing, lapping, and super finishing. These are different types of machining processes. Again, in this type of processes, a physical method is used to remove the material. However, the shape of the cutter is different. The shape of the cutter is different. We often make use of abrasive particles or ceramics in order to remove the material. And of course, the precision and also surface finish which can be resulted from these processes are significantly higher than the ones that can be achieved from using traditional machining operations. Okay, any questions on this? Broaching? I didn't. I said that I am leaving it to another part of the lecture, which I'm going to talk about it. So we will have some examples on broaching and what it can do for us. It's a very interesting process indeed. We will have that covered in the lecture today or maybe next week. It will be covered in machining processes. Okay. Well, here we can see a number of. Here we can see the picture of a number of parts. The one at A is a rotational part, which is often produced on a lathe or a turning machine, because the general configuration is rotational. That's what we already know, right? If the general shape of the part is rotational, then the first candidate for machining that part is turning. However, if the general configuration of the part is non-rotational, like the ones that we can see in B, do we choose turning to make that part? To machine that part? B? Well, not just the whole part, I mean. We've got to make use of other processes, such as milling and drilling, to make the geometry and also the holes. Still, we've got some other methods which can be used in order to make these parts. For example, shaping, planing. These are the methods that can also be used in order to make prismatic parts, the ones which are not rotational. But of course, milling is a well-known process which can be used in order to bring this part to final shape and geometry. For example, here we've got some other types of parts. The one at D, it's easy to say which method can be used to make it. The one at D. We've got to make use of a lathe to make it, but still we've got to make use of some other machines in order to machine some of the features on it. For example, as you can see up here, there is a slot. You see the slot right here. So the basic process for making this part is turning. However, after turning, we've got to make use of other machines, such as milling, for example, to machine the slot on it. And we've got to make use of a drilling machine, maybe, to make the holes on it. So, as we can see, for a large number of parts, we cannot make the part on a single machine only. we've got to make use of a number of machine tools in order to make the part. That one, A. Which method can be used to make that one? A. Of course, milling. Plus some other methods which we will have those methods covered in this unit. That one, a gear, a flat gear. Which method can, which machine can be used to make that one? EDM. It's a very expensive method, but you can make it. That's true. But it's expensive. Okay, that one, milling is the basic machine to be used to make that one. How about this one? The one at E.
With type of milling.
Correct. Milling and some other accessories. Okay? And that one, the one at there. Which method can be used in order to make that one? Say that again? Milling and drilling. I don't think we can make it. Drilling can help, but we cannot bring it to the final shape and geometry. For making those slots, still we are having problems.
We need EDM only because of sharp.
Not only, but EDM can make it. Okay? EDM can make it. What is EDM? Electro discharge machining. By making use of electrical energy in order to remove the material. In this method, the method that he's referring to, a wire is used in order to cut the material which has got electrical charge on it. So it cuts the material. We've got to make the hole first on the workpiece, then pass the wire through the hole, and then make the hole in order to cut the material, which works well for so many processes. Particularly for making high punches and dies in press working. EDM is widely used. EDM can be used for this, but that's not the only method. So, I am leaving this question for now, because once we have covered all the machining processes, I'm going to go back to this slide again and ask you the same question. I'm expecting you to be able to tell us which methods can be used to make every one of these parts once we have covered all the machining processes. Yes, that produces a fine surface finish. Yep, EDM. But anyway, that's costly. So we leave this question at this stage, and then we will be back to this slide once we have covered all the machining processes. Well, why machining is important? It's been listed here. We can make use of a wide variety of shapes. High accuracy, high surface finish. It's very well known to engineers, machinists, etc., etc., and it can often be used to machine any type of material, not just metallic materials. And it does give us good dimensional accuracy and surface finish. As a consequence, engineers know machining processes very well, right? Okay. Let's move on. Well, here we can see a number of machining processes. Here we can see a number of machining processes, starting from A, where a rotational machine part is being produced, and if you take a look at the cutter, it makes a straight motion, which is called feed, in order to bring the part to final shape and geometry. And it's the workpiece which rotates, which can be performed on a turning machine, right? How about the one at B? Again the same, a straight motion of the cutter, however, on an angle. And the part is rotating. Now, a conical part or surface is produced. And the one at C, also the same. We are making a contour or a curve on the surface by the motion of the cutter. However, the way that it moves is not straight anymore. It is following a profile. All these methods all these machining processes can be produced on a lathe. In the bottom tool is the cutting tool which is rotating. Of course, these processes cannot be done on the lathe, but they can be done on the milling machine. Right. Well, Now let me ask you something. These are all categories under generating shape, meaning that part geometry is determined by field trajectory of the cutting tool. It's the motion of the cutting tool which decides the final shape and geometry of the workpiece, right? Now let's move on to the next slide. How do we compare these ones with the ones that we had in the previous slide? Again, we've got the cutters, we've got the parts. Here it's the workpiece which is rotating, but the cutting tool is making a motion along a direction which is perpendicular to the axis of rotation. Here, again, this time it's the cutting tool which is rotating, it's the drilling process, and the part is stationary. And here, it's the workpiece which is stationary, and the cutter passes through it. This is called broaching. You ask me what broaching, right? This is the broaching process. In the broaching process, as you can see, a hole is initially made on the workpiece. And then the broach, which is the cutting tool, passes through the hole just like that, and it is pulled from one side to the other end. When the whole broach or the cutter passes through the hole, what is left on the hole is the shape and geometry of the broach. Okay? However, please note that there are a number of cutting edges, a large number of cutting edges, 50, 60, 100, or even more. And every cutting edge takes a small cut, very small cut. Just the same as a hacksaw. Every cutting edge takes a very small cut, right? But when you move it, they add up to one another, and eventually they take a big cut. Same process is used here. There are a number of cutting edges with different sizes, but the geometry of each one of them is slightly different from the previous one. So every one of them takes a small cut, meaning that in the beginning we've got a hole which is round. The first two cutting edges on the side take a very small cut, and the one after it takes a little bit deeper cut, deeper, and eventually what is left is a really deep cut. This is called broaching, and the cutter is called a broach. Okay? So the one that we had in the previous slide, the hole with a number of slots on it, can also be made by making use of the broaching process. However, the number of cutting edges will be more. This method costs us much less than EDM. Much less than EDM. Because a physical process is used in order to cut the material, which often costs less than chemical or electrical or other forms of energy. Okay? It's interesting, isn't it? Broaching is a very interesting machining method. Anyway, now let's compare these ones with the ones that we had in the previous slide. Here, as you can see, part geometry is created by the shape of the cutting tool. In other words, if you take a look at the shape of the workpiece, it tells you something about the shape of the cutting tool, which is used to make the part. The geometry of the cutter is left on the workpiece. Take a look at that one, at this one, and at that one as well. The shape which is machined is telling us about the shape of the cutting tool which is used to make it, which wasn't the case in the previous slide. Notice that? There is a difference between the two. That's why these methods are actually named processes which are used, which are categorized under forming to create shape. Forming to create shape. The form of the cutter, which is used in order to bring the part to final shape and geometry. Now let's move to another slide here. And let's compare these two figures with the ones that we had in the previous two slides. Is the form of the workpiece, which is machined, telling us something about the shape and geometry of the cutter which is used to make it? Is it telling us something about it? It is. Take a look at the geometry which is machined, then take a look at the cutter which is used to make it. It's somehow telling us about the shape and geometry of the cutter. However, it's not exactly the same. It is similar, right? For example, in that one, a T slot is made. But the cutter which is used to make it is rotational. The slot is not. However, the geometry of the cutter is left on the workpiece. So it is somehow telling us something about the shape and geometry of the cutter. The same as here. Here, a thread is machined, but to some extent, the shape and geometry of the cutter is left on what is machined. It's not exactly the same, but it is similar. So what we can say that in this method, which is forming and generating, we've got a combination of the previous two. In the first one, we have generating. In the second slide, we had forming. Now we have a combination of forming and generating of machining features. Right? So the geometry which is left on the workpiece is determined by the shape of the workpiece and its motion, its feed trajectory. Right? Well, so we can put any machining feature under one of these three categories, which is a combination of the motion of the workpiece and the cutting tool plus the geometry of the cutting tool. These are the deciding factors which determine what we get after machining process is completed. Well, let's skip this one. Here we can see a turning process in order to familiarize ourselves with terminology of the turning process. Of course, we know that we've got a rotational workpiece which rotates on the machine, and we've got a single edge cutting tool which takes the cut from the material. And as you can see, this cutting tool itself has got a linear motion which is called feed, and F stands for feed. For every rotation of the workpiece, which the cutter makes a specific amount of motion along the feed direction, which can be adjusted on the machine. And also the depth of cut, which is the amount of penetration of the cutting tool onto the surface of the workpiece, can also be adjusted, which is called depth of cut or lowercase d. The initial dimension, the initial diameter of the workpiece, which is rotational, is defined by capital D, or sometimes D0. It's the same. D0 or capital D refers to initial diameter of the rotational workpiece. Don't confuse this with final D, which is left on the workpiece once it is produced. DF stands for final geometry. Okay? And the other parameter which is of importance to us is N, capital N, which stands for spindle speed, revolutions per minute. Sometimes it is referred to as RPM, revolutions per minute. And sometimes it is mentioned as REV, standing for revolutions / minute, per minute. So it's the same. RPM or revolutions per minute is the same. This is important because this is something that we do choosing on the machine tool. As of tomorrow, you will have the workshop activity. Some of you will be working on the milling machine and some other on the turning machine. You've got to decide about the spindle speed, either on the milling machine or on the turning machine. And this is something that you've got to compute on the machine. And a very important parameter in machining, in any machining operation, is V, lowercase v, which stands for cutting speed or velocity. Okay? What does that mean? The definition of cutting speed or velocity is the distance traveled on the surface of the workpiece. Take a look at the cutting tip of the cutter. The distance that it travels on the surface of the workpiece is the definition of the cutting speed. The distance traveled often per minute. So unit time, which is often minute. The unit which is commonly used for cutting speed is meters per minute. Although sometimes you will see millimeters per minute or meters per second or whatever. But the commonly known unit for cutting speed is meters per minute. And this equation here is used in order to relate cutting speed to the initial diameter of the workpiece and n, which is this n. Here in this equation, I should have made it capital N, but anyway, n is the same n. Okay? Revise it to capital N so that you don't get confused in your lecture slides. So n is the spindle speed, which is RPM. D is initial diameter of the workpiece, and V is the cutting speed. Indeed, this n in most textbooks has got lowercase n. But in the textbook that we are using, it is equal to by making use of capital N. It doesn't really matter if you make use of lowercase n or capital N. It's always spindle speed n. Okay? To be consistent with other symbols which are used in this textbook, it's better to revise it to capital N, which I will do it later. Okay. Now let's do a problem on turning by making use of the equation that we had in the previous slide, to see how we can make use of this equation in order to do a problem. I have uploaded these examples on Blackboard as a different file, so that you will have the opportunity of doing the problem here before you take the problem. We've got a cylindrical work part. Its diameter is given 200 millimeters. And length of the workpiece is given 700 millimeters. We want to turn this part. Cutting speed is given. Take a look at the unit of the cutting speed. It's 2.3 meters per second. Sometimes we need to make a conversion of the units. If it is in meters per minute, we are fine. If it is in meters per second, we've got to make the conversion somewhere, maybe here, maybe later on. And speed is given, which is that much, 0.32 millimeters per revolution. And depth of cut is also given, 1.8 millimeters. We are to compute cutting time and metal removal rate. Metal removal rate. Do we have the equations? I have uploaded an equation sheet, which is this one, for this lecture. As you can see, let me just briefly explain what we have got here. We've got the same equation that we had in a different arrangement. The relationship between cutting speed, which is up here, spindle speed, which is N, and initial diameter, which is D or D0. This is the same equation in a different arrangement that we had in this slide, right? Same equation. And here we've got the difference between the initial and final diameter, which is of course 2 times of depth of cut. The difference is between the two. And here we've got FR standing for feed rate, which is N times F. F is feed, which is given to us in this problem. N is something which we can compute by making use of this equation up here. And machining time, which we've got to compute it, is the equation for machining time is given here. In order to compute the time of machining, we've got to have the initial diameter, length of the workpiece, F, which is feed, and V, which is the cutting speed. And material removal rate, which is also given in the final equation. If we want to compute material removal rate, we are in need of V, cutting speed, F, feed, and also D, which is the from cut. Now, by making use of this equation sheet, it's not hard, it's not difficult to compute what is requested, right? Which equation is to be used for that given problem? We are after machining time, material removal rate, the last two equations, right? And in order to get those values, maybe we need to make use of this equation and that type of equation as well. Okay? This is uploaded on my ECU. You can, if you have access to the Blackboard, you can just take a look at it, or you can print it later in order to be used for doing the problems. Always, it's a good idea to have a print of the equation sheet with you when you are doing the problems. Okay, back to the problem.
Did you have the cutting speed equation in meters per minute, and it's different on that one?
Unit depends on what we put it in. The common unit for cutting speed is meters per minute. In this problem, it is given in meters per second, so you can easily just convert it. Or you can leave it like that, but you've got to take care of the unit, which is resulted eventually. Okay? Now, let's see how we can do this problem. This is what is given in black, and in red, this is what we are after. Yes? In the final exam, either you will be provided with an equation sheet, or you will have to bring your own equation sheet. I haven't decided what it yet.
I'm not prepared. We could, bring our own stuff.
Preference is not the same. Different people have different preferences. Okay, that's your preference, but other people think differently. But I think I'm going to allow you to bring your own equation sheet. So once you make your own equation sheet, you know where your given equation is. Okay? But anyway, sometimes when I allow students to bring equation sheet, they bring something different in the name of equation sheet, which isn't actually an equation sheet.
We can.
No, you can't. Of course you can. That's what I'm telling you. In the past, there was an instant when I asked the students to bring equation sheet. Equation sheet, what does that mean? It's very clear. Equation on the sheet. That's what it means. What some students actually had made very small size images of slides, and they had some 200 slides on two pages of the sheet. 200 slides, believe me, that happened. I don't know how they could read those small tiny letters and words, but they could. They managed to read it, and they had the half of the lecture notes written at the time of the exam. This is not something that I'm going to allow you, but an equation sheet is fine, okay? I wanted to put an equation sheet at the end of the lecture, exam papers, but it will be a lot. If I want to include all the equations, it will be a lot. Maybe some 8 or 10 pages. So, and we are not making use of all the equations. So if you do the problems, you know which one of the equations are the ones that we need. And many of the equations are similar. I'm going to show you. Anyway, I haven't decided about it yet, but it will be decided soon. And I'll let you know. So you don't need to memorize the equations. You've got to know which one to be used for a given problem. Okay, let's move on. Okay, this is what we are after. Which equation do we use first? First, we've got to compute those parameters to be used in the equations for the machining time and machining material removal rate. This is the first equation, right? By making use of this equation, because V is given. Look, here I have done the conversion of the unit in the very beginning. It was meters per second, so I simply multiplied this with 60 in order to give us velocity in meters per minute. It's simple, okay? So I have done the conversion of unit in the very beginning, so that I do put the right unit in the equation. Sometimes this is given in millimeters per minute. Then you need to convert it into meters. Okay? Anyway, D is also given, which is that much. It was 200 millimeters. We did the conversion of unit because we've got meter on the top. We've got to divide it by meters again. What is left is spindle speed in revolutions per minute. In revolutions per minute. If this is the cutting speed, then we need to compute feed rate. What is given here is millimeters per revolution. What we are after is feed rate, which is unit is millimeters per minute. How can we do that? If we know n, which is number of rotations or revolutions per minute, and multiply it with f, then we can compute feed rate. So there is a difference between feed and feed rate. What's the difference? Feed is given the amount of motion of the cutter for one revolution of the workpiece in turning and cutting tool in drilling and milling. Feed rate defines the amount of feed per unit time, which is minute. That's the difference between the two. Okay, now, are we able to make use of this equation for machining time? We've got to compute distance to be traveled, which is given that much, by feed rate. How long does it take for the cutting tool to travel that much? It's easy when we know the feed rate. Okay, so it's the machining time. And then, material removal rate. We've got all the three parameters to be used in order to compute material removal rate, which is about 80 cubic millimeters per minute. What is this telling us, this final parameter? The amount of the material which is being wasted, which is being converted from a useful material to a non-useful material, right? And in machining, we try to increase this figure as much as we can. It's interesting, isn't it? If you can convert more useful material to more non-useful material, you are more successful. That's what you are doing in machining. And you are an efficient engineer then. Otherwise, you are not. Okay? Anyway, we can have a different look at it. If you can cut more material, it means that you are more productive. You are making more useful products as well at the same time, right? Anyway, keep this figure in mind when we are doing problems for other processes and compare it. Any questions on this? Any questions on this? Okay, anyway, now we are familiar with basic machining parameters, cutting speed, spindle speed. Do not confuse cutting speed with the spindle speed. This happens very often in the workshop environment. When students are doing the task, they often do confuse cutting speed with the spindle speed, which is totally different. And when I ask them to write the report, they also do the same mistake in writing the report. They do not know what cutting speed means, which is different from spindle speed. It's different. The spindle speed is the number of revolutions per minute of the spindle. Cutting speed is the distance traveled on the workpiece by the cutter per unit time, which is totally different. Okay? Very different. Which one is more important? Which one is more important of the two? Cutting speed or spindle speed? They are both important, but if you take a look at machining handbooks, often you do see cutting speed, which is mentioned in the textbook or in the machining handbook, not the spindle speed. Because spindle speed is different on different machines. You've got different machine tools, you've got different spindle speeds. But cutting speed always can be decided on the basis of spindle speeds available. Some other thing that we've got to take into consideration in this problem is the spindle speed which we have computed. What is it? The spindle speed that you have computed? About 220, right? About 220, not exactly. Is this spindle speed available on a given machine tool? On a conventional machine tool, it's not. Because we've got certain spindle speeds available on the machine, which is, say, for example, 200, and the next higher spindle speed is 250. We haven't got 219 and something. It's not possible. So, in practice, we've got to see what spindle speeds we've got available, which is close to this, and take that one into consideration. For example, you haven't got 219 and something available. You've got 200. Okay, now substitute 200 in your problem and continue with it. So, which gives you a different cutting speed from what you are using. How does it work? In the textbook, in the handbook, you are not given with a specific cutting speed for an operation. You are provided with a range. From this up to this. This is minimum, this is maximum that you can use for the cutting speed. So if you play with spindle speed, you can still stay within the range. Slightly higher or lower wouldn't make a big difference. Okay? So keep this in mind. However, if you are making use of a CNC machine, any cutting speed is available. Any spindle speed is available on it. On CNC machines, because it is continuous, any spindle speed on a CNC machine is made available. On a conventional machine, it's not the same. You've got to make use of definite spindle speeds. Okay? Good to know. Well, now, I'm going to ask you to name at least 6 operations that can be performed on a typical lathe. You can talk to your partner sitting next to you and try to list 6 different machine operations together. I mean, straight turning is one operation. Conical turning or cut turning is another. Facing is another. So I mean 3. What is left is another 3, okay? Yeah, you can say so, but that's something I'm going to show you the outcome, so please try to do it yourselves. I'm going to show you more than 6, much more than 6, okay? So you are expected to name 6 only, which you can name more, I believe. The answer is in your lecture notes, so please do not cheat, okay? Do it yourselves, think about it, and put it down yourselves. The answer is in your lecture notes, of course. It's easy to take a look at it and say what it is. Who has got 6? Who has got 6? Who has got 6? 5? 5? You've got 6. Good. Okay, who has got? I mentioned 3 of them already. But anyway, the 3 that you could guess easily, those are the ones that I just mentioned. Okay? Who has got 5? You have got 5. Good. Who has got 4? You have got 4. Who has got 3 or less? 3 or less. Yusuf, you have got 6? Okay. Yusuf is busy. Okay. Now you can see 12. You can see 12 different machine processes which can be performed on a turning machine. 12 of them. But if you know 5 or 6, you are fine, okay? I'm not going to ask you to mention all of them in the exam or something. If you know 6, I think that I wouldn't ask more. I wouldn't ask for more. But anyway, that's turning, straight turning, that's conical turning or taper turning. That one is profiling, producing a profile. Here we've got grooving, external grooving, making a groove on the surface. Here we've got facing, taking the car on this side, on the face of the vertex. Here we are facing a groove on the face. We are making a groove on the face of the vertex. Here we are cutting a typical form, whatever it is, depending on the shape of the cutter, which is this. Boring. What is boring? Some people say your lecture is very boring. What is the difference from my lecture? This is another thing, okay? This is the machining process, which is actually internal turning process. There is a hole, you want to take a cut from inside. Then there is a hole. You can use the same machine in order to take a cut from inside, but there is a hole. Drilling, parting, threading, cutting a thread, and that one, narrowing. Do you want narrowing is? Narrowing. If you want to produce a rough surface on a rotational part, a rough surface, which can be used as a handle or something, you can make use of a special tool which has got a roller here, which is a rough roller. You push it in and then you make it rotate. What it does is that it does actually produce some slabs on the surface, making it a rough surface to be used as a handle or something. It looks really nice if you make use of it. Yes, something, if you want to produce a rough surface which is not slippery, then you make use of knurling process. Okay. Do we need to have a break or we can continue? Have a break. It's the movie time anyway. If you want to have a break, I will play the movie after you are back. Okay? Take a break for 10 minutes, please. Then I will play the video. 10 minutes. Okay.
All tools are in single fluid, which is on a slide moving in two directions. Hence it is designated a two-axis lathe.
This is a CNC lathe, okay? This is a CNC lathe.
Turn mill NC turning machines add milling operations to the machine's capability. For milling operations, the work...
Let me explain what this process is. This is a CNC machine which is called lathe turning machine or mill turn. Indeed, there is a machine which can perform both milling and turning on the same machine. As you can see, the part is locked in place in the chuck of the lathe, and at the same time it is being milled by the cutter.
Pieces held fixed or else rotated at a very slow speed while rotating tools, sometimes called live tools, are brought to them. The main benefit of a turn mill lathe is that more complex workpieces can be finished on the lathe and not have to be moved to a second machine tool for additional operations. The sub-spindle CNC lathe uses a secondary or sub-spindle to pick up the work from the main spindle. Another workpiece is then fed to the first spindle, running both spindles at the same time. Automatic screw machines are for high production turning and operate unattended. Cuts on the end of the work are combined with cuts from the side for rapid production. There are single spindle and multi-spindle types. The multi-spindle automatic is the premier high production turning machine. It can machine multiple parts simultaneously with multiple spindles. The 6 or 8 spindles are held in a rotating spindle drum. This drum rotates the spindles to the cutting tools positioned on slides. The CNC Swiss-type automatic is primarily for parts that are long and thin. To generate external features, the bar stock is fed longitudinally by a sliding headstock through a bushing past the radially arranged turning tools. Long, thin parts can be turned without deflection, as all turning is done adjacent to the bushing, which supports the rotating bar. Vertical turret lathes, or VTLs, are commonly used for large diameter round parts, not suitable for holding in the chuck of a horizontal lathe. The work is clamped on a rotating table 2 to 6 feet in diameter. Tools in toolbox or turrets may be fed from above or from the side into the rotating work. Turrets, by far the most common tool holding arrangement on production lathes, can hold from 6 to 14 tools and quickly rotate on command to bring the next tool into position. Turrets accept tool holders which in turn carry the cutting tools. Work is held at both ends between centers, which are pointed conical pins or held at one end by a chuck, a collet, or if an unusual shape, by a fixture. Chucks fit on the spindle nose of the lathe and hold short, large diameter work. There are many types of chucks, and they are either manually or power operated. 3-jaw universal chucks are the most common. All 3 jaws move in tandem to grab a round workpiece, center it, and grip it. Irregularly shaped workpieces may be held in 4-jaw chucks, in which the jaws adjust independently. Collets, which usually seat in the spindle of the lathe, are hollow cylindrical devices with slots along most of their length. A collet opens under its own spring tension and is closed securely to grip the stock. They hold small diameter roundwork on center. Chucks and collets come in many types to suit various workpieces. Taper turning produces a taper along the axis of the workpiece. Tapers can be produced by offsetting the tailstock from center line or by using a taper attachment. Short, steep tapers can be turned using the compound rest. Facing squares up the end of a workpiece. It also finishes the work, or a single diameter to the desired length. Reaming enlarges and finishes a previously drilled hole by removing a small amount of material with a rotating fluted tool of the desired hole diameter. Boring enlarges and finishes a hole with a single point cutting tool, like a turning tool. The boring bar moves along the axis of the part, as in turning, but inside the drill hole. Parting off or cutting off is like grooving, but with the narrow tool advancing to center, causing the finished part to fall off.
Okay, thanks for playing music. Let me turn off my mobile phone so that the same does not happen to me before it's too late. Okay. Well, any questions on the video clip that we had? Okay. Back to the lecture. Well, and for different methods which was referred to in the video clip, as you can see, there are a number of methods of clamping the part onto the lathe, depending on the shape and geometry of the workpiece. Well, okay. Well, this is, of course, the most common method of clamping the part onto the chuck, right? This is what we have seen in the workshop, right? And as you can see, if the shape of the workpiece is non-rotational or it is unusual, then you can make use of the 4-jaw chuck like that or a face plate in order to clamp the part. And in these two methods, that one is used for small diameter long bars, which is a collet to be used in order to clamp the part, and that one, which is making use of a dog and also 2 centers on the 2 ends, is the one which is used in order to clamp the bar from 2 center holes at 2 ends. The difference between this one, for example, this one and that one, what is the main difference between the two, the top two? What is the main difference between the top two? The geometry of the part which is being machined on these two is different. On the one which is using 3-jaw chuck, the part is clamped from outside diameter. Meaning that what you machine will be machined related to the external diameter. The one on the left, the part is clamped from the center holes. So anything which is being machined will be machine relative to the center holes, not to the external surface. That's important, right? Sometimes you have got a very rough and inaccurate external surface, which is not a good basis for actually locating the part. So you don't want to make use of that rough surface or inaccurate surface. You can make two holes at the two ends, and then make use of two holes. So whatever you produce will be centered according to the central axis of the part. That's important. Okay? Good. Moving on. And of course, this is what was explained in the video clip. There are some machines when you can have a number of parts being machined at the same time for mass production purposes. For this given part, there are 6 parts which are being machined at the same time. Each part has got a different machining step. So there is an indexing device which actually transfers part from station 1 to station 2, 3, 4, 5, and once a part passes through all the 6 stations, 6 different machining operations are performed on the part, and it is completed. Is it clear to everybody how it works? There is a part in here, it will be machined, then it moves to second station, third station, fourth station, and once it visits all the stations, 6 different machining processes are performed. Meaning that at any given time, there is one part in each of these stations, and at the same time, 6 different cutting tools are taking the cut on 6 different workpieces. By doing this, we can increase productivity significantly. Okay? Moving on. This is the boring machine which was explained, so I'm going just to pass this. We can do boring operation on the lathe, as you can see here, by clamping the part. As you can see here, the part is clamped on the chart. Here, here it's the bar which is carrying the cutting tool, and it is clamped between 2 centers. The workpiece which is this, is sitting on the support and doesn't rotate. The difference between the two, we are both on the leg. Here, it's the workpiece which is rotating, and the cutting tool is making a linear motion. Here, it's the workpiece which is making a linear motion, and it's the cutting tool which rotates. So 2 different methods which are used for performing boring process on a lathe. But of course, as you see here, there are some boring machines which are specifically designed in order to perform internal turning operation on really big rotational parts. The way that we do the computation of cutting speed, etc., is similar to turning. Very similar to turning. Okay. Any questions so far? How about drilling? Who can say that drilling is the most commonly machining process performed in industry? Who is against this? Nobody, because it's true. 60% of all machining processes, drilling forms 60% of all machining processes. Okay? Even on the turning, you've got some drilling operations. On milling, on any other operation, you are in need of performing drilling operation as well. That's why it forms 60% of all machining processes. 60. 60. 40% is there for any other machining process. Okay? And as we know, sometimes by making use of a drilling machine, we make a through hole just like that, and sometimes we make a blind hole. How do we compute machining parameters in a drilling operation? This is the equation used to compute material removal rate in a drilling process. Okay? And D here stands for diameter of the drill bit, correct. F, as before, is the speed. N, which could be capital or lowercase n, is the spindle speed. Okay? So, and we've got an angle theta which stands for the angle of the tip of the workpiece, which is different for different materials. The most widely used angle for drill bits is, how much is it? The most widely used drill bit angle is 118. 118. Okay? 118 degrees, but anyway, there are some other angles which are being used. That's the most commonly used angle for most materials. And when we are computing the depth of cut, please note that we've got to actually consider the amount of the drill bit which is used at the tip of the cutter, just like that, which is not considered as the whole depth. Whole depth is considered from the top surface up to the end of the hole when we've got the same diameter. When diameter narrows down, it's not considered as part of the hole or cutting depth. So we've got to take this amount of penetration of the cutting tool into consideration. Okay, now let's do a problem for drilling. A problem for drilling operation to see how we can compute parameters in drilling operations. Well, as you see, the angle for the tip of the drill here is 118, which is, as I said, is the most commonly used angle. A drilling operation is to be performed with a drill diameter of 12.7 millimeters. Twist drill in a steel work part. The hole is blind hole. It's blind hole. It's not through. And depth of hole is given, which is 60 millimeters, and point angle is given. Cutting speed, which is V, is given 25 meters per minute. Feed F is given 0.3 millimeters per revolution. We are after cutting time to complete the drilling operation. And then we are after material removal rate or metal removal rate during operation after the drill bit reaches its full diameter. What does this mean? What does this mean after it reaches its full diameter? What does this mean? It means in the beginning, just the tip of the tool is touching the workpiece. It penetrates a little bit and it makes the hole, actually the hole which is made slightly larger and larger. And it takes some time for the drill bit in order to penetrate into the surface of the material in order to reach the full diameter of the drill. So once it reaches that full diameter, it's the time that is taken into consideration for material removal rate, which is increasing gradually. Okay? How can we do this problem? Let's take a look at the equation sheet that we have. That's the equation sheet. Look. From here, we've got equations for drilling. I have mentioned equations for turning up here, okay? Equations for turning start from here, and we had that covered. Now, equations for drilling. Let's take a quick look at the equations to see if they are different from the ones that we have in turning. That one, is it different? Spindle speed equation from the one that we have for turning. It's the same. That one, same. This one, is slightly different. Machine time is slightly different. Look, we've got T plus A divided by FR. FR was in place. On the top we had length, which was L for turning operation. The whole length. And here, the definition for A is an approach allowance that accounts for the drill point angle. The drill point angle, you've got to compensate for that. You've got to take that into consideration, which will be added to the depth of hole. We will have this computed in this problem. And then, that's all. Now let's go back to the problem. Okay. V is given, F is given, we are after Tm and RMR, which is material removal rate. Again, the first thing that we've got is to compute to compute, because V is given, often V is given in the statement of the problem, or maybe spindle speed is given. But if you have one, you can compute the other one. Now V is given. We can easily compute spindle speed, right? Which is N. For this given problem, it is 626.6 revolutions per minute or RPM. Okay, then we've got to compute feed rate, same as before. N times F. We have computed N. Now by making use of this equation, we can compute feed rate in millimeters per minute, which is that much. Next step. We've got to compute the amount of allowance, which is A. How do we do that? We've got the diameter of the cutting tool, which is 12.7. And we've got the tool tip angle, which is 118 degrees, right? Is it possible for us to compute the amount of the allowance, which is considered only for tool tip? From here, from this tool tip, to where it reaches the full diameter, which is here. Can we compute that, how much is the length of this line from here up to here? Can we do that once we have the angle, we've got the diameter? Yes or no? Possible. It is possible, yes. It is very possible. Which is computed here. By making use of the equation which is given here, if you know a little bit how, say, mathematics and also trigonometry, you can compute it easily. If you don't, just make use of this simple equation which is given here. We have got D, which is the diameter of the cutting tool. We've got theta, which is 180, which is the tool tip angle. Okay? By making use of this equation, if you play with it a little bit, you realize how it works. I'm not going to spend time on this. If you put this in place, then you can easily compute the amount which is to be considered for the tool tip, which is that much. Now this amount of A has to be added to the depth of cut, because up to that much, which is 3.82, it is just making the penetration until it reaches the full depth. So it's not considered as the depth of hole. Now this should be added to D, which is D plus A divided by FR. D stands for depth of cut, depth of hole, and A stands for the extra allowance. Then we've got to divide it by feed rate, which we have already computed. Having this computed, we can easily compute the amount of the amount of time which is needed in order to make the hole, which is the full length plus that much. Okay? Now what else to be computed? Material removal rate, the equation that we just had in the previous slide. Just substitute the values, it gives you the material removal rate for this operation, which is significantly higher than the one that we had for the previous problem. Of course, the geometry is different, but the amount of material removal rate is high in drilling. That's what it is telling us compared to turning. So you see, equations are very similar in any machining operation. Not any in conventional machining operations. Equations are very similar. There are small differences in some of the equations. Most of the equations are similar. Cutting speed and spindle speed relationship is always the same, it doesn't change. The difference in the cutting speed equation is that instead of turning in the cutting speed equation, we substitute diameter of the workpiece for capital D. In here, the diameter refers to the diameter of the cutting tool instead of the workpiece. That's the difference that we've got to take into consideration. What I mean is that up here, for D, what we have substituted is the diameter of the drill bit, not the workpiece. In the previous problem, it was the diameter of the workpiece. Okay? So we need to keep this in mind. Any questions on this problem? Easy or hard? doing machining problems? Easy or hard? Very easy. It is, believe me. And that's something that you've got to do in the workshop for the surface roughness. You've got to do the computation of workpiece, which is, cutting speed and spindle speed. A simple equation, same equation will be used. Same equation will be used in order to do the computation. Okay. Okay, now please help me to see. Not much time there. What operations can be done on a drilling machine? On a drilling machine, what operations can be done? Only drilling, or some other operations as well? What else? What's that? Mining? Milling, you mean? Yeah, some sort of milling. Spot milling. Spot milling can be done on it. What else? Boring.
You can put a drill on one end.
I wouldn't say no, but it's not commonly used for boring purposes because accuracy of a boring machine is much greater than a drilling machine. The accuracy, precision. What else? Drilling? Yeah. Threading. Thread cutting or tapping, yes. Let me show you different operations which can be performed by making use of a drilling machine. Of course, after drilling, this is reaming. Now we know what reaming is, right? We had that in the video clip as well. And tapping is cutting internal thread. There is a solder number here. Are you familiar with tapping solder? Whenever I pass that solder, I remember this operation, believe me, which is internal thread cutting, tapping. Well, and different types of, say, operations, counter boring, counter sinking, which are often used in order to make room for the tip of their bolts and screws in making dies. And that one is center boring, actually drilling. Center drilling is used often when we want to make a really big hole. So we want to put the drill bit in the right place. First we make a center hole, then we change the tool, then we put a big, large, say diameter drill bit, and we place it all at the same position, which is very accurate. Otherwise, we might make a hole which is really big, but it is not accurately positioned in place. And that one, which is spot facing, which is often used on casting processes. If you want to make a small milling to make a flat surface, then you can make use of a drill bit to make that happen. Okay. And two typical drill presses which are used in industry. That's a very little size drill press. We've got this type of drill presses in the workshop. I don't know if you have seen it. When you go to the workshop, you can see this one. We've got a number of these type of machines. And these are often referred to as sensitive drill presses as well, because the operator puts his arm on the lever and pushes it down. And while he senses when the drill bit is taking the car, and then it is completed. Because the amount of the force that you need to apply is significantly lower when the hole is completed. So it's called sensitive drill press as well. In this type of machines, the workpiece has to be really small, so that you can move it on the table and make the ball in the right position. It's the workpiece which moves on the table, so it must be small and lightweight, so that it can be moved easily. Sometimes some type of jigs or special devices are used in order to make the hole at the right position. How about the other one, the one on the right? What is the difference between the two, left and right? The one on the right is a radial drill press. What does that mean? This machine is used for really big workpieces. To make a hole on really bulky workpieces, really big ones, which cannot be moved easily. So that if you need to make holes on different positions, what do? As you can see, there is a column here, there is an arm on the column, and there is the actual drill spindle on this arm, which can slide along the arm, in and out. Also, the arm itself can rotate above the column. It's automated. You've got to make use of a button to make it moving in and out or rotate it above the spindle. What does it do then? It makes it possible for you to move the spindle to any position on a plane, so that you can move it easily in and out and rotate it, and you can make holes at any given position. And it is very accurate and very solid and very tricky. So for very bulky workpieces, when you cannot move the workpiece, you put the workpiece in place, you don't move it, you move the spindle instead of moving the workpiece. That's the difference between the two. Really big parts, the little ones. Okay? Good. Well, let me play a video clip for drilling, then I am leaving the milling operation for next session.
A drill is a round end cutting tool with one or more cutting edges and one or more straight or helical flutes. Drills with two edges and flutes are by far the most common. Drill types include helically fluted twist drills made of either high-speed steel or carbide, and indexable insert drills, which have steel bodies with one, two, or more carbide inserts. Carbide drills are stiffer than high-speed steel drills, so deflection is less, cutting speeds are faster, and holes are more accurate. Carbide drills are especially useful in hard or abrasive materials. Solid drills of high-speed steel or carbide dominate applications up to about a 5/8 inch or 20 millimeter diameter. Spade drills and indexable insert drills cover the larger size ranges. The twist drill is a roughing tool with two cutting lips. The three essential parts of the twist drill include the shank, the flutes, and the point. The shank is the means by which the drill is held and driven. Twist drill shanks may be straight for use in collets, and keyed, or keyless type drill chucks. Shanks may also be tapered for mounting directly into machine spindles or sleeves which fit in spindles. Flutes let coolant into and carry chips out of the hole being produced. Both of these functions are essential for the drill point to continue cutting under the severe conditions of rotating at high speed in an enclosed space. The helix angle of a drill's flutes can vary dependent upon the material to be drilled. A standard helix angle of 25 to 33 degrees is optimal for steel and cast iron. A high helix or fast spiral angle of 35 to 40 degrees is used for low-strength materials like aluminum, and a low helix or slow spiral angle of 15 to 20 degrees is used for drilling brass and plastics. The drill point, which does the work of metal cutting, is formed by the two cutting lips and the chisel edge. Even though drilling is the most common metal cutting operation, the majority of drilling is not performed on drill presses or other dedicated drilling machines. Most hole making is accomplished using lathes, machining centers, high production transfer machines, or almost any machine capable of providing a relative rotation between the workpiece and cutting tool. The sensitive drill press is a low-powered drilling machine used for drilling one hole at a time in small workpieces with small diameter twist drills. The manual feed gives the operator the feel for the operation, which is why this machine is called the sensitive drill press. Although this drill press used to be a common device in most shops, it has now largely been replaced by the more versatile knee mill for most manual, low-volume hole-making operations. The radial drill is used for drilling in large workpieces. It has the flexibility to reach surfaces that cannot otherwise be reached easily. The arm, which moves up and down, carries an adjustable position drill head that can be raised, lowered, and pivoted around the column. Gang drilling machines consist of two or more drilling machines mounted on a common base or table. Often, these machines are operated sequentially, with each spindle carrying a different tool, and workpieces moved from one spindle to the next. Self-feeding drilling units operate automatically for repetitive work. once the stroke, speed, thrust, and feed have been set. They can be used for reaming, tapping, or other operations as well as drilling, and can be mounted singly or in groups. In mass production, most drilling is done with multi-spindle machines or drilling units with anywhere from 2 to 10 or more individual drill spindles. Rotary motion from a central source is transmitted to the multiple spindles. The layout, with the positions and distances set between the individual spindles, is designed to fit a specific part. NC drill and tap centers are like lightweight machining centers, dedicated to hole making rather than milling. The tool changer is usually equipped with 12 to 20 tools, allowing multiple operations to be performed on single or multiple holes.
Okay, any questions so far? Well, I have uploaded a number of, say, problems similar to the ones that we did here. I'm asking you to take a look at the problems and try to do the problems by making use of the equation sheet, which I have uploaded, and the sample problems that we had in today's lecture. And next week, we will be doing machining operations problems and what is left of the machining operations lecture. And today, after 15 minutes of break, we will be doing some problems of casting operation which was delivered last week. Thank you very much for your participation and see you after the break.